So what's this shape called? It's called a trapezoid. So the official definition of a trapezoid is it has one pair of parallel sides. So this is called a trapezoid because this is parallel to that. And we're supposed to find the area of this. I'll need to give you some numbers in a second. How do you find the area of a trapezoid? Probably don't remember. Something weird, yes. Something to do with the bases, that's good. What are the bases in this picture? The parallel sides of the bases. Okay, so let's say that's 10 inches and this is 8 inches. Then the bases are 10 and 8. Okay, so Rebecca kind of reminded some people, she said bases, so what is the formula? Yeah.
The bases added together and divided by 2 multiplied by 1.
Good. Base 1 plus base 2 multiplied by the height, and then, as she said, divided by 2, or you could multiply by a half, doesn't matter. So 1/2 times height times base 1 plus base 2. That's the area of a trapezoid. So this is kind of weird because the bases are not on the bottom. The bases are the 2 parallel sides. And then this here is 5 inches, let's say. The height then is 5 because the height is the distance between the bases. Okay, so this area would be 1/2 times 5 times 8 plus 10. 8 plus 10 is 18. So 1/2 times 5 times 18. So 45 square inches. Okay, so that was not calculus, right? That was just geometry. But we're going to use this geometry to do a little bit of calculus. That's in section 5.5. So let's remind ourselves of what we were doing. We were finding area under a curve. And sometimes we did an approximation called LRAM. And when we did LRAM, we chose the height on the left. And then sometimes we did RRAM, where we chose the height on the right instead. And sometimes we did MRAM, where we chose the height in the middle. So those were approximation methods. They weren't the exact area. They were approximate area. LRAM, RRAM, and MRAM. So today we're going to learn another approximation method. And we're going to use trapezoids instead of rectangles. So here we have a rectangle, and RRAM and MRAM were also rectangles. But for the trapezoidal approximation, we're going to do this. We'll find the area of that trapezoid. And that's called capital T. That's the trapezoidal approximation. So we already have LRAM, we already have RRAM, we already have MRAM. Today we're learning a fourth approximation method called trapezoidal approximation. And the abbreviation for that is just capital T. Okay, so remember this crazy notation means find the area underneath x squared from 0 to 8. And when you write it like this, that means find the exact area. But instead of finding the exact area, we're going to approximate this. So the directions are going to say approximate using 4 trapezoids. Okay, so I'm going from 0 to 8. So if I'm going to go from 0 to 8 and use 4 trapezoids, and if I want them to be equal width, how wide should they be? 2. You just take the 8 divided by 2, right? The fancy way to do that is 8 minus 0 divided by 4 equals 2. The reason I show you that is because sometimes it was over n. Not today, don't worry about that, but sometimes it was over n. Okay, so each should have a width of 2. So you should go from 0 to 2, and 2 to 4, and 4 to 6, and 6 to 8. So you'll have one trapezoid running from 0 to 2, another one running from 2 to 4, one running from 4 to 6, one running from 6 to 8. Okay, so I'd like to start with this trapezoid, the one that goes from 2 to 4. How would I find the height at 2? Square it, just because the function is x squared, right? So 2 squared is 4. So I have a dot there at the point 2, 4. And then at 4, 16. And then I'm going to draw a trapezoid in there. And the area of that trapezoid is 1/2 times 2 times 4 plus 16. So I left a space, right, because I didn't do the first one yet. I'm going to go back and do the first one last, because that's the weirdest one on this problem. Okay, so for the next trapezoid, 6 squared is 36. So then that trapezoid would look like this. Then you take 1/2 times 2 times 16 plus 36. And this one, 8 squared is 64. So we take 1/2 times 2 times 36 plus 64. Okay, now I left this first one for last on purpose because it's kind of weird. 0 squared is 0. So this trapezoid looks like this. It's really a triangle, right? But you could still treat it as a trapezoid. You could take 1/2 times 2 times 0 plus 4. What's the formula for the area of a triangle? 1/2 times base times height, right? So it would be 1/2 times 2 times 4, which is what that is, right? 0 plus 4 is 4. So from here on out, you can just think of a triangle as a trapezoid that has one of its bases 0. Okay, maybe not, but you could. All right, so you add all that up, and I think it comes out to 176. Yes? So this is 176. Okay, so this is not super hard. It's just adding up a bunch of trapezoids instead of adding up a bunch of rectangles. to approximate the area under a curve. And it is just the approximate area, right? Because this curve would actually look like this. So there's some error. It's not the right answer to the integral. It's an approximation to the integral. Okay, so I want to point out that if, hey,
Welcome back.
Happy New Year.
Absolutely. It's a very good year. Right?
Yeah, absolutely. So if f of x is concave down, if f of x is concave down, then t is an underestimate. So what I'm saying is simply, if you have a concave down graph, and you approximate the area under this using a trapezoid, the trapezoid's going to be too small. That's all I'm saying. And then on the other hand, if it's concave up, wouldn't the trapezoid be too big? Yeah. So concave up over estimate. Okay, now we have to remind ourselves, though, how do you find the concavity? How do you figure out if a graph is concave up or concave down? It comes from the second derivative. Okay, so concavity is determined by f double prime. Okay. Let's see what else I got over here. Okay, I'm going to attempt to draw a 3D figure, but I didn't magically become a good artist at the change of the year, so it's going to be bad. Okay, so this is a pond, and the top of the pond looks like this. And unlike most ponds, the bottom of the pond is identical to the top of the pond. So I'm going to attempt to draw this shape again. It's not going to happen. But it's supposed to be identical to this one. So that's the top of the pond. Here's the bottom of the pond. I told you it wasn't going to happen.
So when you say the bottom of the pond, you mean like before?
Yeah, like if you dove into the
Just like a
pond.
pool.
And yeah, so this would probably be better described as an in-ground pool that has a weird shape. No, not an exact oval on the top and the bottom.
Okay.
Yes, sorry. I know you can't tell at all from my picture what I'm trying to say.
Pond-shaped pool.
Yes. Or a pool-shaped pond, whichever. Okay, so now I'm going to make it 3D by putting a couple lines here, but that's not going to work. Yeah.
So we can.
Yeah, who knows? That's why I have to describe it, because my art will not do it justice. Okay, the reason that I needed the top to be identical to the bottom is there's a volume formula that works for figures that have identical tops and bottoms. The volume is capital B times H. And what the capital B stands for is the area of the base. So you might not have known this, but you've pretty much used this formula, even this year. For example, for a cylinder, it has a circle on the top and a circle on the bottom, right? So then the base is circular. So the area of the base is pi r squared. So then this would become pi r squared times h. That's why the volume formula for a cylinder is pi r squared times h. But let's say instead you had a door stop that had a triangle on the top and a triangle on the bottom. You could still use this volume formula, except that would be a triangle. So it would be 1/2 BH times h. So the power of this formula is it's more versatile. You have less to remember. It works on any 3D figure that's identical on the top and the bottom. So it'll work on this, because this is quote unquote identical on the top and the bottom, right? Okay, so let's say that the area of the surface and of the bottom was 90 square feet. And let's say that the height or the depth was 3 feet. Then the volume of this would be 90 times 3, so 270 cubic feet. So far a lot of geometry in today's lesson. Example 1 was geometry, just the area of a trapezoid, and example 3 is total geometry, just the volume of a 3D shape that has an identical top and bottom. Oh, there's something I want to mention about example 2. We set this up so that all the heights were going to be equal, right? We divided the 8 by 4. So that's why this was a 2, that was a 2, that was a 2, and that was a 2. But I don't want you to assume that the heights will always be equal. It's possible on some problems where this would be a 5 and that would be a 7. So just watch out for that. Okay, the next thing I want to point out is if you do LRAM, and then instead you do RRAM. So there's LRAM, there's RRAM. So then, let's say instead you do T, the trapezoidal approximation. What I want you to notice is that line that I just drew to make the trapezoid, it split this rectangle exactly in half. So what that means is that the trapezoidal approximation is the average between LRAM and RRAM. Since that diagonal line split that rectangle in half, the area of this trapezoid is going to be in the middle between the area of that rectangle and this rectangle.
It still wouldn't be exactly as like MRAM.
No, it would not. That's true. Good. So is everybody okay with this? Now Dan brings up a good point, because sometimes the trapezoidal approximation, it's easy to confuse that with MRAM. So I'm going to try to draw you a picture that convinces you that MRAM doesn't equal the trapezoidal approximation. So MRAM, Dan said this, now I'm going to try to convince you that it's true. So for the trapezoidal approximation, I would do this, right? But for MRAM, I would go to the middle and choose the height there. So there you can tell that MRAM and T are very different. Yes?
So of the approximations, is MRAM still the most accurate?
It depends on the function. So to answer your question, I'll draw a couple of functions. Sometimes MRAM is better, sometimes T is better, sometimes RRAM is better. It just depends on how the graph goes. Great question. So here, this is just to show you that MRAM is not the same thing as T. For MRAM, you use the height in the middle, right? In the middle here, you pick the middle x value and take the height. So MRAM is the middle height. Sorry, it's not the middle height. It's the height in the middle. MRAM is the height in the middle. T is the middle height, the average of that height and that height. Okay, so just to, because Rebecca said, is MRAM better than T or is RRAM better than T? So here's a picture that shows you, well here, MRAM is better than T, right? So in this picture, MRAM is a better approximation than the trapezoidal approximation. But in this picture, this is going to be crazy, but trapezoidal approximation would be this, right? But MRAM would be this. So here, T is better than MRAM. Everybody good? Survived your first lecture of 2016? That's all I got.